It's always fun to come to a ICTS meeting because the meeting format is so different that you always get to hear something interesting. So when they invite you, you immediately say yes. And then roughly about 2 weeks before the meeting, you start panicking, saying, because you hear something different, it also means you have to say something different, and it means you actually have to think, right? And that's what I'm going to start with, because if we want to look at EM counterparts to Decihertz gravitational wave sources, I actually had to read up quite a bit about what those sources are and what we'll do in EM. And it's so very different from what we are used to doing for the current follow-up efforts that we do. Okay, so right. So what we have to do today is essentially we wait for something to happen. O4 is the first time there is chance of an early warning, and the early warning is about the time it will take for me to cover this slide. That's it. That's all we get. And if you look at this dense figure here, it shows when was the gravitational wave signal detected and what was the follow-up done in different bands. And the scale here is -100 to +50 seconds. And you can see a lot of the optical follow-up, for example, happened right around the first few days. Radio continued and X-ray continued for a long time later. Okay, so what we currently do essentially is that we all have our units set up to send us alerts whenever there is an open announcement from the GW detector network. And then pretty much we start running around saying, follow up, follow up, follow up. That's pretty much how we do it. The other reason for this is that not only is it something that we have to do on the fly once we get an alert, but these are 10 sky maps from O3. Okay, and bunch of these are actually ones that we followed up with the Growth India telescope. And you can see we are ambitious. This is essentially, I mean, a single antenna pattern, so 26,000 square degrees. Okay, so the localizations are really, really poor. And that is what the community, the EM follow-up community right now is used to. Getting something that wakes you up when you're most wanting to sleep. Or in my case, when I was nicely watching a movie, the first scene of the movie played and my phone went off saying there's a BNS event, which was GW 190426. To rub salt in, it was later retracted. And that just makes it even more fun. But this is what the current follow-up looks like. And that is what all of our efforts and resources are geared up towards. So if that was today, what's tomorrow? Or technically 4 days from now when ER15 will start. And remember that the first source itself was technically discovered in an engineering run, which was later reclassified as an observing run. So what are we doing? Well, we will do everything that we did in O3. So there is still Fermi and Swift. There is still ZTF and PanSTARRS and Growth, Grandma, and all these collaborations, and a bunch of new things that are coming in to actually augment what we have there. Okay, so for example, there is this new survey which has been commissioned called Winter. Of course, we had a great time joking about winter is coming for a long time. Very few Game of Thrones people here, I see. Okay. And then after winter, there is this one being commissioned in Australia. These are both infrared telescopes, wide field infrared survey telescopes. And the advantage here is that the more we started understanding kilonovae, partly because models got better and partly because we got one data point to anchor those models against, we know that they are far more likely to be brighter in redder colors. And we really need to be able to search for them in wide field in infrared bands. So J band, H band, and so on. Okay, so there's nicely one in the north, one in the south. We also realize that UV carries very important information, and UV lasts for a very, very short amount of time, which again means we need wide field telescopes that can respond quickly. UV you can't study from the ground, so you have to put them in space. Two proposals, one is Dorado, one is called Ultrasat. I think Ultrasat is a bit further along in terms of its overall progress. There might be people here who know better about it than I do. But the plan again is a variety of wide field telescopes which are going to study rapid transients. O3 was notoriously annoying for all EM observers because O2 was kind of a full glass. We got EM counterpart, great. And then in O3, there were a lot of events and absolutely no counterparts. And if you simply scale 170817 to the distances of all O3 events, then that's not surprising. We just don't have assets out there which are sensitive enough to detect this. Okay, you have kilonova, if you just from 40 megaparsec, you put it out to 200 megaparsecs, now you are dropping to 24th magnitude, which is fainter than most meter class survey telescopes can go. Or if you take the X-ray and gamma ray part, then Fermi, the discovery paper by Fermi acknowledges, for instance, that if the event was 30% fainter, they would have missed it. So few new telescopes coming up there. China has launched 3 GE cams and 4th launch is planned. These are just hemispherical scintillator based detectors. The original plan was to have 2 of them on opposite sides of Earth, covering the entire sky. SWORM is a French-Chinese mission as well. The original proposed launch was mid-22. They are currently aiming for late 23 launch. And these are both highly sensitive X-ray, gamma ray space telescopes. This instrument here is the wide field instrument, covers about 2 steradians. So still only about 1/6 of the sky. We don't like those odds, right? You wait for a very long time and then there is 78, 18, 85% chance that you were just looking in the wrong direction and you missed it. Okay, we in particular were especially badly burnt by that because Astrosat missed 170817 not because of sensitivity, but because we were on the wrong side of the planet. Okay, the source was Earth occulted. We used that to rule out half of the Fermi localization region because based on the Fermi parameters, we should have had a 10 sigma detection. So we never want that to happen again. So we have our own extremely ambitious mission proposal called Daksha, where the idea is to launch 2 satellites, opposite sides of Earth, very much like GECAM, but a factor of few more sensitive. So in terms of overall reach, the idea is that you have 1 keV to 1 MeV kind of coverage, which gives you more sensitivity than anyone else. So think of it as bat-like sensitivity over the entire sky. For 170817 like events, if you look at this column here, that's the volumetric reach that we have for Daksha, and it is higher than all these other missions existing proposed. Theseus unfortunately is gone, so no more Theseus, but you compare it to SwiftBat, Fermi GBM, or Swarm or anything, you can see that the effective area here is much higher than all of these other instruments. So this is what we are planning. Now the question is that now if we start doing Decihertz gravitational waves, it's likely the same follow-up community that is going to start studying the EM counterparts to those, right? And what can we do there? So thanks a lot that he has set up the talk very nicely. He talked a lot about the sources and everything. More importantly, he was gracious enough to send me his slides in advance so that I could avoid any overlap. And I realized he has covered everything. So my life is very easy. Okay, so now what I can do is I can completely look at the part of actually going to have to observe these things. So we'll start with our staple favorites, okay? First is, okay, at face value, you look at this and life should be easy. You talk to someone who's from the gravitational wave community and they'll tell you, oh yeah, we'll detect these months or even years in advance. We'll give you precise sub-square degree localizations, no more worrying about 1,000 square degree area of the sky. Range, things get a little bit dicey because it depends on which of these detectors you are looking at and what source you are looking at and so on. But in principle, looking at all of this, you should be like, this should be a piece of cake. Take your telescope, point it there. You can actually plan it in advance, go to sleep and live happily ever after. So let's start with our canonical BNS sources, okay? So yeah, they're localized well before merger. Again, the months to years kind of timeline comes in and you have a sub-square degree localization. So a normal telescope with a normal field of view in principle should be able to get this. Range, now that is where you start digging in and you realize maybe life is not going to be quite that easy. Okay, and this is looking, I missed the first 2 days, okay, but looking at the talks today and with some of the interactions I have had here, I thought this is a great chance to put in an observer side rant. As an observer who is interested in following up these sources, what I would like to see is statements of this sort, saying that a source of type XYZ, binary neutron star, double white dwarf, whatever it is, can be detected at a distance d, okay, or up to a distance d. I don't want to know just 3 years before the event. I want to know whether you can tell me that with a month accuracy or a minute accuracy. Because if it is a minute, I can point a highly sensitive telescope there and wait for that thing to happen. If it's a month, then all the time allocation committees are going to be laughing me out. I want to know what the area of this is, and I want all of this in a single sentence, right? I don't want this to be pieced out from 10 different papers at different point. And I also want to know how many times this is going to happen, right? So for an observer to go out and observe this, I want to know when this is going to happen, how often will it happen. Essentially, this is my dream wish list. Someone give me a table of doing this, and the rest of my life becomes much, much easier. This is also how our observing proposals currently do manage to go out for LIGO follow. Because while we are saying we are going to span thousands of square degrees, we know how often it is going to be 20,000 and how often it's going to be 200. This has been a little hard to get for the Decihertz band as of now. Okay, so neutron star sources, well, okay, let's scale from what we know. So prompt gamma rays, if you take 170817, that was about 3 into 10 raised to minus 7 ergs per square centimeter per second. So if you scale it, for example, if you have something like GLOC, then you should be able to see these to high redshift. That is huge. That just blows your mind. It goes down by 5 orders of magnitude in flux. But it comes with this square arc minute localization. So if that delta t error bar on when this is going to happen is small enough, I can actually take Chandra or XMM and point it there and actually get that explosion as it is happening. Right? I can collect photons. If next generation telescopes are up, something like Athena, I can actually get spectra, I can get everything. I don't know yet if we can do this or not. Okay, and this is not even in window timing mode. This was some very interesting experimental work done by these authors last year. The kilonova part gets a bit worse because even at 200 megaparsecs, that's nothing is changing about the kilonova. So it's still going to be 25th magnitude. We will know where to point, and we could find something at 25, 26, but it could be much, much fainter because, for example, one of our results from the growth collaboration is that based on what we did not find in O3, there's no chance that all kilonovae are as bright as 1707. So we know that it seems to be brighter. Not surprising. You always catch the bright, weird outliers first. There is something else that can be very interesting, by the way. So if you want to, so why do you not know a 100-second binary pulsar? And the reason is that there are way too many unknown parameters here. Okay, you don't know the periods of the two pulsars. You don't know their phases. You don't know. So even if I tell you that there are 5 millisecond pulsars, you don't know at what instant the first pulse should come. And then you don't know the orbital period or phase either. Okay, and then there are period derivatives, especially when the orbit is in close, which means that the space over which you have to search. So, we like to think of this as a textbook diagram where there's a radio telescope pointed somewhere and you see a blip and there's a pulse. That doesn't happen, right? You have to fold your data and stack it in before you start detecting these pulses. And over these phase space, you cannot search it. It is computationally impossible to do it. But if you actually get your basic orbital parameters from the GW, if you know the period and period derivative, for example, and so on, then that can actually drastically narrow down. You are essentially cutting down the dimensionality of your search space. And with next generation radio telescopes like SKA coming up, this might actually become accessible. We'll have to put in numbers to see if this is really possible or not, but we might be able to start seeing pulsations from these systems as they are coming in. And if we can lock onto those, then that actually is information that can feed back and forth between the gravitational wave and the electromagnetic community, saying we are actually now refining these orbits based on radio data that we have here. How can that actually fit in? I don't know if knowing the phase of the orbit, for example, is going to help the GW analysis in any way or not, but that can be actually quite an interesting change. Yeah. I don't know the number. No idea. Absolutely no idea. Sorry, if you asked optical or radio, X-ray, life would be easier for me, but I don't do radio at all. Okay, then let's get to the other case, which we have heard a lot more about today, right? Double white dwarfs. And there's a nice keyword there, galactic. That made me happier saying, okay, we can find sources in other galaxies. We saw 1708, 1740 megaparsecs away. Now we are talking of tens of kiloparsecs. We should be able to see everything. And again, you have good localization, a lot of time to do it. Turns out that no, it is not a toy story out there. Okay, so if you look at the galaxy, the sun is placed right here, and this is a 10 kiloparsec circle. And that actually covers a lot of interesting parts of the galaxy, right? This part is boring, but you do encompass the center of the galaxy. And you would think that we should be able to see things out here, but no. It turns out that mass means mass in all forms. So if you have a lot of stars, you also bring in a lot of dust. So there's a lot of extinction here, and you can't see far in those directions. So this is just a random polygon that I've drawn on this, but this is probably more like what our range looks like. To give you an example, yesterday morning, there was a nova discovered by Winter, the telescope that I showed a few slides ago. And this nova was detected in infrared. Okay, these are the galactic coordinates here. It's too hard to see here, but there is a nice image of the Milky Way. Okay, trust me. And if you zoom in, then that is roughly where the nova is located. And right in the galactic plane, this is a very dark part of the sky. And that is because of the extinction there. Okay, so if you calculate the optical band, the G band extinction in that direction is 24 magnitudes. Okay, if you put Vega in that place, okay, or something that would have been visually as bright as Vega, then it gets to the limit of what a 10-meter telescope observes today. That is how much optical extinction there is. Even in infrared bands, there is about 5 magnitudes of extinction. Okay, so this was discovered as an 11th magnitude object in J band. If it was unextincted, and if you could see J band, this would have been a naked eye object. And it is way too faint to be seen by any optical telescope right now. So that's the kind of extinction we see in these directions. And that greatly is going to hamper what we can see. And I'll come back to that in a bit. So coming back to white dwarfs, we've seen a variant of this plot today. This is just white dwarfs in Gaia, and this is absolute magnitude. This is from another paper. Bottom line is that the absolute magnitude of white dwarfs peaks at around 12. So if you take that and put it at a kiloparsec, that's 22nd magnitude. So white dwarfs are faint. This is about the limit of a meter class telescope that you can go in surveys, things like ZTF, for example. And then you put it at 10 kiloparsecs, you are really, really pushing the limits. 27th is hard. And it gets worse because of extinction. A bit better off in IR. Fortunately, the colors of these things are not very strong. So you can see that the absolute magnitude in say K band and V or R band is quite similar. So that's good. So I'll give you some pieces of context here. Okay, so I added this in purposely. This is a old paper that we wrote. This was a neutron star white dwarf system, where this is a 2 solar mass neutron star. So we wanted to know what the companion is. Should be very interesting. We were happy. We have Keck at our disposal. 10-meter telescope went in and imaged, and this is the image. And somewhere here, what you don't see is the location of the neutron star. Okay, which means that is also the location of the white dwarf. So here are the images. This little smudge here is a detection, and this little may or may not be a smudge here is a non-detection. 24.3 magnitude with a 10-meter telescope looking at it. Okay, so that's how hard it is, and this is not in the galactic plane, so this is not heavily extincted. So when you now switch to something which is going to sit in the galactic plane for sure, 10-meter telescopes are not cutting it. And you can say, but wait a minute, we have better. Right? We'll soon have 30-meter class telescopes. So you go and look at 30-meter class telescope capabilities, focused on infrared again, and it takes an hour to get to these kind of magnitudes, even with a 30-meter class telescope. Okay, and if you want to do spectroscopy, then yeah, you can forget the 27 magnitude of. So at best, by spending a lot of time and effort, you are going to get a detection of a white dwarf binary sitting at 10 kiloparsec, if it is not heavily extincted. And you can say, wait a minute, but if you're saying IR is so great, let's go to James Webb. And it doesn't help that much either. Because again, you look at the exposure time calculations and you're, okay, maybe at red wavelengths, 900 nanometers, you can push to about 28, but elsewhere it's not that much better. Okay, so although we will know this with great precision as to where this event is going to be or where the progenitor is, we will still have a hard time doing the multi-messenger aspects of it. And this is not going to change anytime soon, right? We are already talking about James Webb here. We are already including 30-meter class telescopes here. And then comes the other part saying this is just talking about a detection. So what? Okay, so ballpark numbers, we have seen these in the simulations 2 talks ago, that its period is going to be 10 or tens of seconds. We are talking about 1 hour exposure to just get a detection, which means any modulation, any variability, anything that you had is going to be completely averaged up. You are going to see the average photometric colors of the 2 white dwarfs together, or a white dwarf if the other one is a neutron star, which is much, much fainter. Okay, no ellipsoidal modulations. If you get a spectrum, it's going to be the average spectrum of 2 sources. Fortunately, white dwarfs have ultra broad lines already. So this 2000 kilometer per second, if you just assume, say, 0.01 solar radii white dwarfs, which are at contact 1 solar mass each or something, you get something like 2000 kilometers per second velocity. That really doesn't make much of a difference. That's 50 angstroms kind of Doppler shift, and white dwarfs have lines which are much, much broader. Explosion part should be interesting, right? And there, if we keep monitoring, we will see things brightening up. And that is again where that delta T has to be small enough, because if I know something is exploding, I'll try to take shorter exposures. In most of those exposures, I'll see nothing. And then suddenly I'll start seeing something. So knowledge of when it is going to happen and the uncertainty on that becomes quite important. The next topic is again something that should fill us with hope, that supernovae, the range of our galaxy, should make life easier. So same diagram again, same 10 kiloparsec circle. I'm sorry, for a post-lunch talk, this is a bit too depressing, but can't help it. Hopefully you're already asleep. Okay, so supernovae life is great. 1A peak at -19, you just apply distance modulus and they should be the brightest thing in the night sky. Okay, magnitude of -4.3, even at this distance of 10 kiloparsecs. And indeed, historically, there have been a few naked eye supernovae in the galaxy that have been seen. But again, extinction, remember the nova, yesterday's nova that I talked about, we can have extremely huge extinction. And this is where the problem comes in again. Okay, most of the mass in the galaxy is sitting in this line of sight. And that mass means more stars, but also more gas and dust. So this is also the area which is not accessible to us. So the prediction was right that the next supernova we'll see it in neutrinos or gravitational waves. Maybe some chance in seeing it in infrared, but very unlikely that we are going to see a galactic supernova in optical or infrared. That said, it's great to make a statement like this because nature really likes to mess around with us. So if I say something like this, hopefully the universe will be angry enough and it will give us a supernova right here. And we might see it. Okay, what about high energy? Now, high energy photons don't get extincted quite as much. And there I just stole numbers from Jan's paper saying that what happens if you have a single degenerate supernova or a double degenerate supernova. And in both cases, you can get a very bright flash. So I'm again putting sources at 10 kiloparsecs to just have a sense of scale. The peak flux is going to be order of 10 raised to -2 ergs per square centimeter per second. There was a GRB in on 9th of October 2022, which has been dubbed BOAT, brightest of all time, and was special enough that APJ had a special issue dedicated to just papers on this gamma ray burst. And that one, the peak flux was about 10 raised to -5. The total fluence was about 10 raised to -2 over a very long episode. Okay, so we are talking about this supernova being much, much brighter than anything before. That means two things. A, everyone will see it. And B, the fact that no one has seen it tells you that nothing has happened in the last couple of decades. It gets even brighter if you talk about a double degenerate model where the peak flux can be much higher. For reference, by the way, with this flux, the ionosphere of the Earth actually responded. And people who do atmospheric monitoring saw this change in flash ionization of the ionosphere. So if we are talking about this kind of flux, you are probably talking about radio blackout for a short duration. Okay, so really intense supernovae, which means again, even before we put space telescopes to monitor this, in early radio days also we would have noticed. Interesting side effect for this, yes. Yes. So interesting side effect of this, by the way, is that all these small CubeSats are the only ones which will not be saturated by this flux, because everyone else is designed to have very, very high sensitivity. This is, I think, my second last slide. These IMBH and intermediate mass ratio and so on, we really don't know what the EM signal is. So if we know where to look, we'll put in some time and effort to find some things. Supermassive black holes have been identified as binaries based on some modulation, but it's a hit or miss. So that's it. I will end here. Since I'm not yet doing Decihertz, I'm advertising our project again. Go check it out. And hopefully we have time for some questions.
Thank you very much for this great talk. Other questions? Let's start up there.
Wait, oh, okay, you can hear me now. Thanks, it's a very illuminating talk, especially from someone who's not in the EM side. So I had a question regarding early warning. So one of the things that that we've heard over and over in this talk is that Decihertz will give us like very large early warning, possibly months, maybe year. Now, one of the signals that we expect as a precursor are these fast radio bursts. It's still not clear whether CBCs will produce fast radio bursts, but there are certain models which say that at some point in the inspiral, it will produce an FRB. Now, since these models don't exactly tell you when it will happen before the merger, and say you're given an early warning time of a year, the challenge then is, of course, in very practical terms, you can't have a telescope sitting there and waiting for a year for it to happen. So how would you target an event like this when you don't know when it will happen?
So that is where this delta T concept comes in, right? Realistically, based on what resource you are looking at, there's a time scale over which an observation is scheduled. If you want an optical telescope to sit on something for a few hours, that's trivial, right? If I have an X-ray telescope and you ask for a few days, that's also possible. If you start asking for months, then that's not going to happen. So it's not really a question of that T, and that can get refined, by the way. So if you tell me today that there is a merger that will happen in 2025, and then in mid-24, you now narrow it down to a window of a week, that also helps. But without that delta T, and I've unfortunately not come across a single delta T value in the limited research that or literature survey that I did, but it's that delta T that's going to make all the difference.
Yeah, I got that. I think there is an additional level of uncertainty here, which is also coming from the model, because the model itself.
See, that part is fine. Once we know the error windows on all of that, then proposals can be tuned accordingly. Okay, so for example, if you are talking about resonant shattering of the crust, then your uncertainty, even if it is a order of magnitude uncertainty, still translates to a day. Because before that, the sources are so far away that you are not sweeping into that frequency range at all, right? So that's not a big problem. On any of these, by the way, order of magnitude is good enough on any of these parameters that I'm asking. But until we know that, we can't really commit to whether observations will be useful or not. And more importantly, a time allocation committee will not give time.
Are there other questions? Maybe.
Hi, thanks for the great talk. I had a question about the extinction. And so when you report magnitude values, do you subtract a background of the dust already, and that's when you report the magnitude?
Extinction is not a background that you add on to. So the values which are reported. So for example, when this nova was discovered at 11.3, that's the observed magnitude. What we know is the amount of flux that will have been absorbed is an estimate. And that estimate is based on observations of other things in that area. So we very rarely, until you do detailed observations of an object itself, it is very hard to get a precise value of extinction. And extinction in terms of flux is an exponential. So a small error in your measured value can make huge differences in the flux level.
And so what do you think are the prospects of making those errors much smaller as we?
It is not an error. Extinction just means that the source appeared 100 times fainter in J band than it should have, and it appeared 10 raised to 10 times fainter in G band than it should have. That's what 24 magnitudes of AG, 25 magnitudes would mean. 10 raised to 10 times. So if 10 raised to 10 photons left the source heading towards you, one will reach you. We can't do anything about it until we get a very large vacuum cleaner. Right? So that extinction is something which you can't get rid of. It's not a measurement error.
Thank you so much.
Okay, another question? If not, let's thank Varun again.
Thank you.